and I apologize in advance. I had a cold last week and I had this lingering cough. The cold's gone, so I don't think I'm contagious, but I might, if I start coughing, I apologize, because it's always a bad thing when you have a microphone and you start coughing. So, yeah, the Internet of Important Things. All right, so there's a lot of hype these days around this term, the Internet of Things. It's, to me, what the field is about, Internet of Things, is about using Internet technology to connect things. Seems like a reasonable thing to do. So, some of you may have seen this chart before. This is a chart that is updated each year by Gartner, which is a media organization, where they call it their hype cycle. And so they're tracking various emerging technologies. And they, for 2 years running, they put the Internet of Things right at what they call the peak of inflated expectations, which, according to their model, will inevitably be followed by the trough of disillusionment as people realize that, well, you know, technology is maybe needs a little more time to mature. So there's no question there's a lot of hype about this. I mean, you talk to interact with companies, you know, there are people at the boardroom level using Internet of Things buzzwords without really knowing what it means. So the hype is there. But the field's actually not that new. Not even the term. In fact, the term Internet of Things has been used fairly commonly in Asia for probably about 10 years. You know, it really only recently caught on in the U.S. And there's various other terms that have emerged that really are referring to very much the same thing. So in Germany, for example, they've been talking about Industry 4.0 for several years. It's really about, you know, connecting everything industrial to networks. One of my favorite terms comes from Cisco, FAW. What they mean by that is it's kind of like a cloud, but closer to the ground. So it's interacting with the physical world instead of just being an information technology. So the key thing here is the interaction with the physical world. That's actually what is the interesting thing about IoT and about all of these disciplines, is that it's a cyber-physical interaction. It's the cyber world coming into contact directly with the physical world. In fact, we've been doing this for some time, okay? Even using Internet technology to solve cyber-physical system problems. So one of my favorite examples is this printing press from Bosch Rexroth. This is a big machine. So this is, you know, in the space of industrial automation. It's a machine about half the size of this room, and it does print on demand. So if you go and you buy a copy of Lee and Sechia from Lulu, it'll get printed on a machine like this. The one copy you ordered, right? Gets printed on this machine and gets packaged up, bound, etc., all by the machine. Now, the interesting thing about this machine is that this particular version, which Bosch Rexroth started producing around 2008, in a major departure from practice in industrial automation, they used Ethernet and TCP/IP for the network. So these yellow cables here that you see are Cat5 cables, and they're connecting hundreds of microcontrollers that are orchestrating hundreds of pieces of machinery. There's, in operation in this machine, the paper is flying through the machine at about 100 kilometers per hour. They're depositing ink onto this paper with micron precisions. They have an amazing system where the paper comes from a 2-ton roll that's about 2 meters in diameter when it's first brought in. And when a roll of paper starts to run out, they bring in a forklift, second roll, put it on a secondary spindle, spin up that spindle to match the speed of the paper that's flying through the printing press, and then just before the old paper roll runs out of paper, a flying paster, they call it, comes in, lays down double-sided tape, glues the new paper to the old, and launches it into the printing press without shutting down the printing press to rethread it, okay? amazing piece of orchestration. And by the way, this gets done in such a way that the scene falls between pages of whatever's being printed. Okay, so very tight orchestration, a lot of software, a lot of networking, a lot of communication, a lot of safety issues, right? These are safety critical systems. If things go wrong, they can go really badly wrong. So you really have to design these things very carefully. And in industrial automation, the idea of using Ethernet and TCP/IP would have appeared at the time to be patently absurd to most people in the field. And yet they did it. I'll talk a little more about how they did it, okay? But the key thing is that this is an example of the use of internet technology in a cyber-physical system. In my opinion, the term IoT actually includes in the terminology the solution to the problem, not just the problem. It suggests that, well, it's internet technology we should be using. But that's not necessarily the only possible solution. So I actually prefer to use the term cyber-physical systems for the problem. The problem is, how do we orchestrate computation and networking with physical dynamics? And I'm particularly interested in systems that are safety critical, like this printing press, like the airplanes that we fly on, and so on. And these are the systems that I call the Internet of Important Things. And so the question, the burning question in IoT in my head is, how can we take a technology that was designed originally for information processing and use it for cyber-physical systems? And there's potentially enormous advantages to doing that. In the case of this particular printing press, they don't actually get most of the advantages that they could get because this network is isolated. In fact, part of the way that they achieve the levels of reliability that are required to make this machine work is they segregate this network from the internet, air gapping it. You lose a lot of the potential advantages of networking a system when you do that. So one of the challenges here is, how can we in fact deliver systems that are safety critical like this, but actually are on the network and can be interacted with remotely. So this is a big problem. It's an extremely rich research area. And one of the things that I really like about doing research in this area is that cyber-physical systems are full of contradictory requirements. So, contradictory requirements. We want adaptability, but we also want repeatability. We want high connectivity, but we also want security and privacy. We want high performance, but we also need low energy for many of these systems. We want asynchrony because these systems are physically distributed, but we need coordination and cooperation. We want these systems to scale up, but we want reliability and predictability. These are all contradictory requirements, actually. On the face of it, it would seem that you can't actually satisfy both, but we can actually. In fact, contradictory requirements are really a driver for innovation. The research enterprise thrives on contradictory requirements. You should look for contradictory requirements in your research, because that's where you're going to be able to do the most innovative things. In my opinion, cyber-physical systems require a whole new set of engineering methods and a whole new set of engineering models. And this is really what I'd like to focus this talk on today. What should those engineering methods and models be for cyber-physical systems? So let's focus on models, okay? Now, there's a lot of talk in engineering communities about model-based design. And many people who work in on the problem of model-based design will try to make you believe that it's a new approach. It's not, okay? Design has always used and will always use models. The use of models is not new. The use of models at the level of the models that are shown here might be, okay? But the use of models per se is not new. And to emphasize that, let me just show you a model, okay? I don't need the sound for this. That is quite old, okay? 300 years old, and widely used in engineering, okay? Differential equations. Differential equations are models that we use to describe physical dynamics, okay? They're not graphical models, so when you think of model-based design, you don't necessarily need for your models pictures. They can be expressed in symbols or words, as well as in diagrams, okay? The issue when you're using models is to always understand what your modeling framework is. In this case, for this example, the modeling framework is calculus and Newton's laws, okay? The pair of equations shown there is just saying F equals ma, okay, which everybody learned in high school physics. The model is distinct from the thing being modeled. The thing being modeled is some physical system. And unfortunately, engineers often conflate these two, okay? They mix up in their head the model and the thing being modeled. One of my favorite ways of expressing this problem is due to Solomon Wolff-Lulem, who said, "You will never strike oil by drilling through a map." It seems obvious, but engineers do this all the time. You talk about your C program as if this was the implementation, not the model. It's not the implementation. It is a model. A program is always a model, okay? The implementation is electrons and holes sloshing around in silicon, okay? So you're always using models when you're doing design, always. I want to emphasize that this statement does not in any way reduce the value of the map. Maps are still useful, even though you can't get oil. Okay? Now, let's talk about cyber-physical systems, because I'd like to focus on what kinds of models should we use to build and design cyber-physical systems. So here's a simple schematic of a very small version of the printing press. Okay? You've got some physical plant that you're driving with actuators that are digitally controlled. You've got some software running on a microprocessor. You've got a network fabric and another microprocessor. Okay, so this has all of the elements of sort of a various minimum interesting cyber-physical system. It's got the computational elements and the microcontrollers, the network fabric, and the physical plants. And I emphasize the closed-loop dynamics here. Right, you have actuation of the physical world and sensing of the physical world that is then being used to further actuate the physical world. So we're interested in the overall closed-loop behavior, closed-loop dynamics of these systems. So the question is, what kind of models should we use for these kinds of systems? So as with any intellectual discipline, you don't want to have to start from scratch. So we should look at, well, what are the best available models that people use today for pieces of the system? So for the software side, well, software is a model, okay? Think of one very powerful modeling paradigm, single-threaded imperative programs. Single-threaded imperative programs have a very nice property, determinacy, okay? Now, I'd like to claim that, in fact, some of the most valuable models that are used in our engineering toolkits have this property, they share this property. Determinacy is actually a very valuable property of models. So a model is deterministic if you know the initial state and you know the inputs, then the model defines exactly one behavior. Okay? So knowing the inputs and the initial state is enough to know what that behavior will be. So deterministic modeling frameworks have proved extremely valuable in the past. I'll give you 4 examples. Okay? First one, single-threaded imperative program. I already mentioned it, right? If I define a procedure in C, this model defines exactly one behavior if I know what the input is and the initial state. In this case, there is no state information in this, so it's just a function of the inputs. Okay? Now, one of the things that inevitably when I talk about this, people walk out of the room saying, wait a minute, did Edward say that non-deterministic models are not useful? I didn't say that. I will not say that. Okay? In fact, I'll give you an example here where a non-deterministic model could be extremely useful. I could construct an abstraction of this simple piece of C code that is a non-deterministic model that describes the behavior of this over all of the possible inputs. There are 4 billion possible inputs, by the way. Okay? So An exhaustive search of the deterministic behaviors would require me to explore 4 billion possible behaviors. I could instead take this deterministic model, abstract it using a non-deterministic model, and then prove formally that line 8 never executes in this program. Okay? Proving that by doing an exhaustive search over the 4 billion inputs would be much more painful. Non-deterministic models are useful, but notice that in this particular case, the value of that non-deterministic model is actually predicated on the determinism of the underlying. Okay? The determinism of the underlying model is extremely valuable. Trust me, we would not be doing electronic banking if single-threaded imperative programs were non-deterministic. We just would not be doing that. Okay? So, but it's a model that's deterministic, right? Knowing the input, it defines exactly one behavior. What about the implementation? Well, the implementation is actually not deterministic. Okay? It's electrons and holes sloshing around in silicon. Line 8 could, in fact, execute. An alpha particle could come in and flip a bit in my program counter, and line 8 will execute. Okay? That doesn't undermine the value of the model. The fact is that we have learned how to make physical implementations of this model that are extremely faithful to the model. With very high probability, the physical implementation will behave as the model specifies. Okay? I want you to notice there's a turn of a phrase there that is a little bit odd. Okay? I'm asking the physical system to behave like the model. I'm not asking the model to behave like the physical system. Okay? There's a difference. Now, that particular family of deterministic models, single-threaded imperative programs, relies on another family of deterministic models that has also proved extremely valuable historically. Instruction set architecture. These were invented by IBM in the 1960s in order to be able to create families of computers that could all execute the same software. Okay? It is a deterministic model of the behavior of a machine for which there are many implementations, all of which are non-deterministic. Every computer is non-deterministic. Okay? The instruction set architecture, however, is a deterministic model, and once again, we have learned how to make extremely reliable realizations of physical systems that behave like the model. How do we do that? Well, we rely on a third deterministic modeling framework, synchronous digital logic. Synchronous digital logic is a deterministic model of an underlying non-deterministic system. And the determinism of the model is extremely useful. Even though we're talking about electrons and holes sloshing around in silicon, being able to rely on the logic gates actually doing what you've specified in your logic diagram is an extremely valuable property. We can analyze these models in ways that we cannot analyze the physical system directly. Okay? 3 examples of deterministic models that have proved extremely useful historically. In fact, I would argue that these 3 deterministic models, single-threaded imperative programs, instruction set architectures, and synchronous digital logic, account for the information technology revolution. It wouldn't have happened on the time scale without these 3 deterministic models. Okay? Now, what about the physical side? Deterministic models are also useful on the physical side. I talked about differential equations before. These have been used for 300 years to model behaviors of non-deterministic systems. And by the way, they're used even, you use deterministic models even to manage uncertainty. Okay? So, for example, a control systems engineer designing a feedback control system can analyze the robustness of a system, which means what are the margins of stability? How much do the parameters have to vary before the system becomes unstable? Okay? So you have uncertainty about parameter values, but you use a deterministic modeling framework to analyze that uncertainty. The determinism of that modeling framework is an extremely valuable property. It's not to say that there isn't value in non-deterministic models. I'm not saying that, but I'm saying that there is enormous value in deterministic models. Now, here's the question. For CPS, what happens when we take the best of class deterministic models from the cyber side and put them together with the best of class deterministic models from the physical side? We get non-deterministic models. Every time. Today. We don't have deterministic models, at least not in widespread use, for this combination. Okay? If we want the next information technology revolution to happen, or the next industrial revolution, we're going to have to fix this problem. Okay? Now, it's probably nagging. Determinism, really? I mean, cyber-physical systems exist in a physically complex world with lots of uncertainty. Shouldn't we just accept that uncertainty and say, well, you know, we really should be building our models all around uncertainty and all around non-determinism? So here's the one, I'm going to make the one point that I hope is the major takeaway from this talk. Okay? And to most people, it's obvious in retrospect, but it's a little bit of a surprise when you first hear it. So the question is, what is the value of models? So in science, the value of a model lies in how well its behavior matches that of a physical system. Okay? That's a litmus test that scientists apply to models. They're not very useful if they don't match what the physical system does. But in engineering, the value of a physical system lies in how well its behavior matches that of a model. In engineering, we actually create the physical system. In science, you're given the physical system. In engineering, we create it. And it's incumbent upon the object created to match the model, rather than the other way around. Okay? These are very different uses of models. And by the way, they're beautifully complementary. And I believe personally that you can't do good engineering without doing science. So if you're doing good engineering, you're going to use both styles of modeling. But you're using them in different ways. Okay? If I come up with a synchronous digital logic model of a system, and the semiconductor fab guys give me something that doesn't behave like my model, I'm going to go to a different fab. I'm not going to blame my model. Okay? If I were a scientist, I would blame the model. So in engineering, model fidelity is actually a two-way street. It's not always just incumbent on the model to match the physical world. It's also incumbent on the physical world to match the model. Now, of course, for a model to be useful, we have to be able to construct a faithful physical realization. We've learned to do that with these cyber models that I illustrated before. We know how to make physical implementations of synchronous digital logic that will perform a logic calculation perfectly 1 billion times a second for years. It's an extraordinary achievement to have gotten the physical world to behave like that model so faithfully. Extraordinary achievement. Okay? So here's a model of Newton's cradle. You can tell that this is a model and not a physical system because it's just too perfect, right? Here's a version of Newton's cradle that I bought from Amazon for $6, including shipping. And it's a piece of fact. Okay? So, to a scientist, the model is flawed. To an engineer, the realization is flawed. I should have been willing to spend more than $6 on Newton's cradle, and maybe I would have gotten something better. Okay? And I'm an engineer. I actually think we can make better Newton's cradles, and that we shouldn't blame the model for not behaving like the physical system in this case. Okay? So we need to change the question for CPS. The question is not whether deterministic models can describe the behavior of cyber-physical systems with high fidelity. If you ask that question, I would say, yeah, the answer is no. There's too much uncertainty. But there's a different question that I think is a more useful question. The question is whether we can build cyber-physical systems whose behavior matches that of a deterministic model with high probability. And this is where I believe our research agenda should be, is in showing that this question can be answered in the affirmative. I think that will take CPS to the next level, when we can give the affirmative answer to this question. Okay? Now, Okay, well, what about resilience and adaptability? Well, I already mentioned that, a control system engineer uses a deterministic model to study the margins of stability of a system. But that principle actually applies very broadly. Deterministic models don't eliminate the need for robust fault-tolerant designs. In fact, I would argue that they enable such designs because they make it clear what a fault is. If your model defines one behavior, given the inputs, anything that doesn't deliver that behavior is an indication of a fault. Something in your system did not behave as expected. So as soon as you've got a deterministic model, you now have a principle under which you can detect faults. And detecting faults is an essential prerequisite to handle. Faults will occur, always. The physical world will deliver faults. So you've got to design systems to handle them, but you have to be able to detect them in order to handle them. So it's clear to me that we have to fix the models, because we've got this best-of-class cyber models, and we've got these best-of-class physical models. They're deterministic in isolation. You put them together and the results are non-deterministic. That's a problem. So how do we fix it? So what I'd like to do is spend the remaining time just giving existence proofs that this can be done. Okay? We actually can come up with deterministic models for cyber-physical systems for which there are faithful physical realizations. I don't want to pretend that my solutions are in any way comprehensive. In fact, I'm sure they're not. Right? I think this is a very rich research area, and probably many of you will go off and invent things that are more powerful than what I'm going to describe. But what I will describe is something that shows it can be done. Okay? So the essential problem that I'd like to address is the source of non-determinism when you combine these cyber models with the physical models. One of the key sources is a property of software, which is that the correctness of an execution of a program is not predicated on how long it takes to do it. The time it takes to do something is irrelevant to correctness. In computer architecture, people talk about it being a performance problem. Okay? And better performance is better, but it's not a correctness problem. So it's not part of the determinism of the model, how long it takes to do it. That is an essential property of essentially all of the software that we use today. Okay? And of course, when that software interacts with the physical world, if we use a deterministic model like a differential equation to describe the dynamics of the physical world, that deterministic model is all about temporal dynamics. When the actuator kicks in, has an enormous effect on the behavior of the physical system. Okay? So we take these two deterministic models in isolation, put them together, and the result is non-deterministic because the software side doesn't say anything about when things happen, and the physical side reacts to when they happen. Okay? So we have to fix this problem. Today, we've been designing reliable embedded systems for some time. Right? If you fly an aircraft today, these are cyber-physical systems, and they're astonishingly reliable, really. The fact is that if you look at how these systems are designed in practice, we will ultimately look back on this engineering practice in embedded systems as being horrifically primitive. Okay? The way people design embedded systems today is they write some software, they deploy it on a microprocessor, and they measure it on the bench to see what it does. And then they put that subsystem together with another system and measure what it does. And then put that together with another subsystem and measure what it does. And you can do all kinds of analysis on the software. Formal methods people will prove safety properties of the software. It won't tell you anything about the dynamics of the system as implemented because it doesn't include the timing. Okay? So the timing, in fact, emerges from the physical implementation. And once you have the physical implementation, that's when you know what the behavior is. In other words, you're not using models, right? You're just building physical systems, and hacking, it is hacking. You're hacking a physical system, and the behavior of the physical system emerges from the hack, rather than being designed. That's the problem we have to fix. By the way, one of the stories that I heard that really underscores the essence of this problem came from a guy at Boeing who had worked on the Boeing 777, which was Boeing's first fly-by-wire aircraft. It started flying around 1995. Okay? And he told me a horrific story. He said that Boeing expects to make the plane for about 50 years. The plane is still in production. It started being produced in 95 or so. Started being flying in 95. Right? They expect to be still making them in the year 2030. When they started production of this plane, they bought a stockpile of all of the microprocessors that they expect to use for the entire production run of the plane. Okay? So a Boeing 777 rolling off the production line in the year 2030 will use microprocessors that were made in 1992. And those microprocessors are currently stored in liquid nitrogen to try to slow down the diffusion process, the natural diffusion processes in the silicon, in some hopes that the microprocessors will still work in the year 2030. To me, this is a profound embarrassment to computer science, right? That the only way we can create software that will behave the same way in 2030 is to freeze the microprocessors in 1992. That's nutty, right? We can fix that problem. I'm convinced we can fix that problem. So, if you embrace temporal semantics, you can do amazing things. And you can do this at levels above the simple software level. So, in the case of Bosch Rexroth, they used Ethernet and TCP/IP. Ethernet was originally designed to be able to share a wire among a bunch of uncoordinated users of a network, allow them to collide with one another electrically. Right? These two devices